Okay guys, welcome to Engineers Academy. Kindly subscribe my channel if you haven't subscribed it yet. Now we are going to solve this problem related to the centroid of the composite bodies. So again we are given this composite body and we are asked to locate the center of mass of the assembly shown. The conical frustum has a density of 8 megagrams per meter cube. So this whole composite body consists of a truncated frustum cone which is cut here. So here it is consist of a cone and a hemisphere. So the density of the cone is given, that is 8 megagram per meter cube, and the density of the hemisphere is given, which is 4 megagram per meter cube. And further it is said that there is a 25 mm radius cylindrical hole. So here we have a cylindrical hole of height 100 mm. So if we look into this whole composite body, so we can divide this whole composite body into 4 different subparts or different segments, right? So if we look into this, so first of all we can consider this whole cone without any cut, right? So one segment could be this whole cone. Then we can consider this one another cone which is cut out from this whole cone, right? So this is the second segment. Let's say this is the second segment, and then the whole can be considered as the third segment. This is the third segment, let's say, and the hemisphere can be considered as the fourth segment. This is the fourth segment. So we divide the whole composite body into these 4 segments, and we know the location of the centroids of these 4 segments, right? For these 4 segments we need to develop this table, that is segment, then mass, z tilde, and z tilde times mass. So z tilde is the location of the centroid of each segment from the origin along the z-axis. Further, if we look into this whole composite body, so it is symmetrical about the z-axis. So from that we can say that the centroid or the center of mass of this whole body will lie on the x-axis somewhere, on the z-axis somewhere, since it's symmetrical about the z-axis. So from that we can conclude that the x bar and y bar of the center of mass of this composite body will be equal to 0. So we only require to find the z bar. So we need to find the z bar, since this whole composite body is symmetrical about the z-axis. So we can write that z bar will be equal to, from the principle of moment equation, we can say that z bar will be equal to the summation of z tilde times m divided by the total mass. So now what we need to do is that we need to find the product of z tilde times mass for these 4 segments, and then we need to find the total mass, and then we need to apply this equation, then we will be able to find that z bar. Now if first of all we need to find the height of this cone, this small cone, since this truncated cone, this frustum has a height of 100 mm. So if I draw that height here, if I mention that, so let's say that somewhere here we have that height, and from here to here this height is 100 mm, which is given. But since we are considering this whole cone, so we need to find this height as well, right? This is 100 mm. So this height is, let's say, y, which is the height of this small cone, right? Let's say this is y. And as we know that the radius, here the radius is 50 mm. If I draw one another line here, if this is the cross section of that cone, that cone is a 3D cone, remember, right? So this radius is 50 mm. This radius is 50 and this radius is 25. This is given, this is 25. So this height is y and this height is 100 mm. So these two triangles are similar triangles. This triangle, and this triangle, these two are similar triangles. So we can apply the properties of similar triangles. So if we apply the property of similar triangle, then the ratio of the corresponding sides will be equal. So if we consider this whole large triangle, then 100 plus y is the perpendicular. We can write that 100 plus y divided by this base, which is 50. This will be equal to this y for the small triangle. This small triangle, this is y divided by 25. And if we cross multiply, so we can write that 100 plus y divided by y will be equal to 50 divided by 25, and 50 divided by 25 is 2. So this is 2. And again, if I multiply y on both sides, so we will have 100 plus y equals to 2y. And if we bring this y to the other side, so that will become negative. So this is 2y minus y. So 2y minus y is y. So y, from this we can say that y is equal to 100 mm. So from this we have determined the height of this smaller cone, which we need to subtract, right? Since that volume is not present, so we have to subtract the mass of that while considering the calculation. So but the height of that cone which need to be subtracted is 100 mm. Now we are given that the density for the cone is 8 megagram. So we need to have the density in kg per meter cube, since all the dimensions are given in mm. So we need to convert this into kg per mm cube. So if rho c is given, the density of the cone is given as 8 megagram. So 8 mega is 10 raised to the power 6 gram per meter cube. We need to convert it into kgs per mm cube. So 1 kg is equal to 1000 grams, or we can say 10 raised to the power 3 grams, and 1 meter equals to 10 raised to the power 3 mm. So 1 meter cube will be 10 raised to the power 3 cube, or we can say that this will be 10 raised to the power 9. This is 10 raised to the power 9 mm cube. So this will cancel out and gram will cancel out. So we will be left with the units of kg per mm cube. So this is 8 into 10 raised to the power 6. And this is 10 raised to the power 3 into 10 raised to the power 9. So this is 10 raised to the power 12 kg per mm cube. So if I bring this to the numerator, so that will become 10 raised to the power minus 12. And 10 raised to the power 6 multiplied by 10 raised to the power minus 12. So this will give us 10 raised to the power minus 6. So this is, we can say that this is 8 into 10 raised to the power minus 6 kg per mm cube. So this will be the density of the cone in kgs per mm cube, remember. And similarly, the density of the hemisphere will be 4 into 10 raised to the power minus 6 kg per mm cube, remember. So now let me write that rho c is 8 into 10 raised to the power minus 6 kg per mm cube, and similarly the density of the hemisphere is 4 multiplied by 10 raised to the power minus 6 kg per mm cube. Now to find the mass of each segment, as we know that density is mass divided by volume, so mass of each segment will be density of that corresponding segment multiplied by its volume. So that will give us the mass of each segment. So now let's say that this is our segment 1, the full cone. So let me write that the full cone is segment 1. Then we have to find the mass of segment 1. So the mass of segment 1 is m1, and that is the full cone, and the density of the cone is this rho c. That will be rho c times its volume. So the volume for the cone is, as we know that is 1 divided by 3 pi r square into h. This is the volume of the cone, remember. 1 divided by 3 pi r square h. So if I put all those values in this equation, so rho c is 8 multiplied by 10 raised to the power minus 6 in kg per mm cube, multiply by 1 divided by 3 volume, 1 divided by 3 pi r square. So the radius of the cone is 50. This is given. So from here to here, this radius is 50. If we consider it in 3D, this is the cross section, so its radius is 50 mm. So I will write this as 50 square and its height is 100 plus y. If we are considering this full cone, then the height is 100 plus 100, so that is 200. So that is multiplied by 200. So this will give us the mass of the full cone, that is the segment 1. So this is 8 multiplied by 10 raised to the power minus 6 multiplied by pi multiplied by 50 square multiplied by 200 divided by 3. So this gives us 4 divided by 3 pi. Let me write that the mass is 4 divided by 3 pi, and this is in kg. If we simplify this, so this is 4.189 kgs. So the mass of the segment 1 is 4.189 kgs. So this is, in short, we can write that this is 4 divided by 3 pi. Now the location of the centroid of this full cone. So if we consider that, let's say if this is my axis, if this is my y-axis and this is my z-axis, so its centroid is, the centroid of this cone is, let's say, located somewhere here. Let's say this is the location. So this is z tilde. The location of the centroid from the y-axis is z tilde. And as we know, the location of the centroid of the cone is the h divided by 4, that is the height divided by 4. So the height of this full cone is 200 mm, that is 100 plus 100, that is 200. So z tilde will be 200 divided by 4. So for this, if we say that z tilde 1, this is the centroid location of this segment 1, so it will be 200 divided by 4. So that gives us 50. So this means that the centroid of this full cone is at a distance of 50 mm from this y-axis. So I will write that this is 50. From this table, we can see that if we are considering a cone, then its volume is 1 divided by 3 pi r square h, and its centroid is at a distance of h divided by 4 from its base. So we are using these formula for calculating the z tilde of the cone. So that is h divided by 4. So h divided by 4 is 200 divided by 4, and that gives us 50. So z tilde 1 for segment 1 is 50. Now we need to take the product of this. So 50 4 divided by 3 pi into 50. This gives us 200 divided by 3 pi. So this is 200 divided by 3, or we can say that this is 209.44. This is not mm square. The units of this will be, this is not right. This is mass times mm. The unit of the mass is kg, and the unit of the tilde is mm. So this is kg mm. So this gives us 200 divided by 3. Let me write it is 200 divided by 3 pi. Now segment 2, this is segment 2, the second small cone, but since this is not present in the real body, so we have to subtract this. We have to subtract the mass of this, right? So we need to put minus sign here, and then we need to find the mass of this segment 2. So the mass of the segment 2, again I will use this formula. This is the mass of segment 2, and we are considering this as a part of this cone. So we will use the density of that cone as well. So that is 8 into 10 raised to the power minus 6. And the volume of this small cone is, again, we can find it by using this formula. So that is 1 divided by 3 pi. Now the radius of this small cone is 25 mm. This is 25. So that is 25 square into h. The height is 100 mm, right? This height is 100 mm that we have just calculated using the properties of similar triangle. So this is 100. So this will give us 8 into 10 raised to the power 6. I will put this as 100, the height is 100 and the radius is 25. So this gives us, so this is 1 divided by 6 pi, so let me write it as 1 divided by 6 pi. And now the location of its centroid from the y-axis is, so its centroid will be located somewhere here, and again we know that this distance will be from that table, this distance will be h divided by 4, and now its height is 100 and 100 divided by 4 will give us 25. The height of this is 100, so 100 divided by 4 is 25. But this cone from the y-axis is, this cone is at a distance of 100, this is 100, this distance is 100, so 100 plus 25, so that is 125. So I will write this as 125. The location of the centroid of this small cone from that y-axis is 100 plus 25, so that is 125. Now 125 multiplied by this this answer multiplied by 125, so this gives us 125 divided by 6 pi. So this is 125 divided by 6 pi, and since this is negative, so this will also be negative. Now the third segment, this is the second segment. Now the third segment is the hole. Again, the material is absent, so we need to subtract the mass of this hole as well. So this is segment 3, and again we need to put minus sign here. And now the mass of this hole, this is cylindrical hole. So as we know that the volume of the cylinder is, pi r square h. Pi r square is the base of the circular area at the bottom multiply by the height, so that is pi r square h. So again, since it's the part of the cone, so we will use the density of the cone, that is 8 into 10 raised to the power minus 6, and volume is pi, and the radius of this hole is 25 mm, since it's given that the radius is 25 mm for the cylindrical hole. So that is 25 square, and the height is 100. Remember, the hole has a height of 100 mm, so I will multiply it with 100. So this is 8 multiplied by 10 raised to the power minus 6 multiplied by 25 square multiplied by 100. So this gives us, and then we have to multiply it with pi. So this is 1 divided by 2 pi. So this is 1 divided by 2 pi, and now it's the location of its centroid. So its centroid will be at its mid height, so its centroid will be somewhere here. So its height is 100, so the location of the centroid from the y-axis will be 50, that is 100 divided by 2. So this is z tilde for segment 3. So z tilde for segment 3 is 50, and now we need to multiply it. So 50 multiplied by 1 divided by 2 pi is minus 25 pi. So this is minus 25 pi. Now the fourth segment is that hemisphere. So the mass of the hemisphere, the fourth segment will be, this is the mass of the third segment, remember, this is the mass of the third segment. So the mass of the fourth segment is again rho of hemisphere multiplied by volume of the hemisphere. So rho of hemisphere is 4 into 10 raised to the power minus 6 kg. So 4 into 10 raised to the power minus 6, and the volume of the hemisphere. So for the full sphere, the volume is 4 divided by 3 pi r cube. So for hemisphere, we need to divide it by 2. So that will be 2 divided by 3 pi r cube. 2 divided by 3 pi r cube. So this is 2 divided by 3 pi, and the radius of the hemisphere is this radius, that is 50, this radius. So this radius is 50. This is 50 cube. So this is 4 multiplied by 10 raised to the power minus 6 multiplied by 2 divided by 3 pi r cube, that is 50 to the power 3. So this gives us 1 divided by 3 pi. So that is 1 divided by 3 pi. So this is the mass of that fourth segment, that is the hemisphere. So this is the fourth segment. Its mass is 1 divided by 3 pi. And from table, the location of the centroid of a hemisphere is at a distance of 3 divided by 8 r from its base. This is 3 divided by 8 r. So we can find that let's say that its centroid is located somewhere here. So this distance will be 3 divided by 8 r. So 3 divided by 8 r, and the radius is 50. So 3 divided by 8 multiplied by 50. This gives us 18.75. But as we can see that the origin is somewhere here and its centroid is somewhere here, so it is in the negative z. So this distance is 18.75, but it is in the negative z, so we have to put minus 18.75. So this is minus 18.75. And now if I multiply this 18.75 multiplied by 1 divided by 3 pi. So that is 25 divided by 4 pi. So this is 25 divided by 4 pi. Now we need to find the sum of z tilde times m. So we have to add up all of these, and we have to add up this mass. So the total mass is, let me write that the summation of mass will be the sum of this, that is 4 divided by 3. 4 divided by 3 minus 1 divided by 6 minus 1 divided by 2 plus 1 divided by 3. So this will give us 1. So from this we can say that that is 1 pi, right? So this is pi. The mass is equal to pi, that is 3.142 kgs. Now the summation of this, so this is the summation of, we can write that this is the summation of z tilde times m. So we can add up all of these, so that is 200 divided by 3, but remember that this product is negative. This is minus 18.75 into this, so this is minus. And now when we add up, so this is 200 divided by 3 minus 125 divided by 6 minus 25 divided by 4. So that gives us 175 divided by 12. Or I can say that this is 14.58 pi. This is 14.58 pi, right? We have added all of these without the pi. So at the end we need to multiply all these with pi. So that is 14.58 pi. And now z bar is equal to the summation of z tilde times m divided by the total mass. So we can write that z bar is 14.58 pi divided by the total mass, which is pi kg. So this is cancelled out, so that is 14.58 mm, and this is along the positive z axis. So this means that the centroid of this whole composite body is located somewhere here from the origin, and this distance is 14.58 mm. So this is the solution of this example from Hibbeler statics. I hope this will help you in your learning. Do let me know in the comment section if it helps in your learning. Also subscribe my channel if you haven't subscribed it yet.